Hi there, this is part 2 of my repair attempt of the advanced DMM2 multimeter. If you recall, in part 1 I traced the problem that the meter would not run when powered from mains to bad contacts in the AC-DC switch, and after cleaning that problem was fixed. Then I fixed the dark second Nixie digit by replacing a bad transistor in the multiplexing circuit. The missing digit was working again, but the leading one digit was still not working. This was a defect driver transistor, and after replacing it, everything came to life. I then did a calibration of DC volts, ohms and AC volts, and all was fine until a day later AC volts stopped working. So let's continue the tale from there. Taking it apart again, I quickly narrowed the problem down to the AC-DC converter. Interestingly, it would work when shocked with freeze spray. Watch the scope when I do. The output before rectified is the blue signal, which is supposed to be 10 times of the input, which is the yellow trace, but I set the scope so that the yellow trace is 200 millivolts per unit and the blue trace is 2 volts per unit, so they appear with the same height. As the board warms up, the output distorts and degrades, which causes the readout to drop more and more until it reaches 0. This is the AC-DC converter schematic, which is on a separate board. Over the course of a Sunday of troubleshooting with repeated application of freeze spray, the duration while it worked became less and less until it no longer responded at all. I was hoping the culprit was TR2 because when applying the freeze spray to IC1, TR2 got a healthy dose as well. But TR2 and TR3, both BC107s, measured still okay using base emitter and base collector diode test, but I replaced TR2 regardless. That had no effect on the problem. I also replaced C11, which was supposed to be 20 microfarad, but showed just slightly below 5 microfarad and a rather large ESR. That did not fix the problem either. The sad conclusion was that IC1 had given up the ghost. That chip is an SL701C, and if you are a long-term follower of my channel, you may be experiencing a déjà vu. The Wainker B642 autobalance bridge had two SL702C, of which one was broken. The SL701C and the SL702C are basically the same chip, with the SL701 having an internal Zener diode that's missing on the 702. As I found out already during my repair of the B642, these chips are very rare and expensive, and I asked Dave, the owner of the DMM2, if he wanted to proceed. He did, and he even bought that chip and sent it to me. The chip that came was a SL701B, which is actually a better version with less input offset voltage than the original SL701C. The AC-DC converter is a separate board, and to replace the chip it had to be removed. It is soldered in with 5 connections, and I could not get it out by desoldering. You can just make out 4 of the connections down here. In the end I had to cut the connecting pins and then remove the leftover stumps one by one from the motherboard. This is the board after I cut it out. The top is the component side, bottom the solder side. I'm quite amazed how dirty the PCB solder side is. Lots of flux residue everywhere. Same on the main board, by the way. The cut connections to the main board are these 4 here and this one. Basically we have AC in, ground, minus 12 volts, DC out and plus 17 volts. The connections are formed by soldering in stiff wires that kind of thread through the PCB, starting on the component side, diving to the solder side, coming back to the component side before going off board. Redoing these will not be an easy job, but first the IC has to be removed. Also not the easiest job. The PCB seems to be made for an 8-pin dual inline chip, and the pins of the round ICs have been bent to fit that pattern. After 2 hours of work, the IC was out. Sadly, despite working very carefully, I lost 2 pads completely, and the others are just about still hanging in there. The pads just detached from the board, taking even part of the track with them. It really seems the fragility extends to the PCB tracks as well. This is still repairable. And by the magic of YouTube, the new chip is in and the board is repaired, using 2 jumper wires to connect the pins that have lost their pads and tracks. I tried to remove as much as possible from the flux with isopropyl alcohol, but it proved pretty stubborn, and after the experience with the lost pads, I did not want to use any sort of brush. I was tempted to drop the whole thing into an ultrasonic cleaning bath, but I wasn't sure if that wouldn't be too destructive as well. Anyway, I tested the board outside the DMM2, and the repair and the new chip worked fine. From the component side, it looks much prettier. By the way, I tested a dual inline socket as it fits perfectly into the holes. I was tempted to put it in and insert the SL701 into the socket, but in the end I decided against it. For one, this will over time cause contact problems, and more importantly, the SL701 would end up way too high. This section of the board is covered by a closely fitting shielding can, which does not leave any room for putting things in sockets. Given the fragility of the board and pads, I decided to solder new connection pins on top of the existing stumps instead of trying to remove the stumps. That may look pretty ugly, but it should work. Now all that's needed is to insert the board with my new pins into the holes of the motherboard and solder them in. After about half an hour of adjusting, I got that done and then reinstalled the shielding cans. And a test with about 1.9 volts AC at the input showed it all worked and was stable. Of course, the AC calibration had to be redone, starting again with a 200 millivolt range and shortening the input to set AC to 0. This time I was a bit smarter and powered the DMM2 using DC from the bench power supply. At least that way there's no danger of accidentally touching mains. And calibrating the 200 millivolt range by applying 199.7 millivolts AC and then 1.999 volts at 800 Hz. Since these inputs are manually adjusted, there's really not much point spending too much time to set generators to produce 199.9 millivolt exactly as input. As long as you have your comparison instrument, you can just set the DMM2 to read the same. Now for the higher frequencies. This is done using trimmer capacitors. The trimmer for the 2 volt range is a trimmer mounted horizontally over the range switches. Despite the service manual stating that this calibration should be done after the meter is back together, but not in the housing yet, I found this to be impossible in practice. You basically have to squeeze past the front plate holes for the switches and then try to find that trimmer screw far in the back. Okay, maybe it can be done if one had a very special non-metallic, extra long and extra thin screwdriver. I don't, so this has to be done while disassembled, even though without being properly back together, the calibration may actually be slightly off. The trimmer caps for the 20 volts and 200 volts can really only be operated once the meter is together, because you have to go through a hole on the top of the PCB to reach the screw. The other side you see here has no slots, so these trimmers can't be operated while the meter is disassembled. And then there is the trimmer cap for the 1000 volt range here. What trimmer cap, you may ask? That twisted piece of white wire is the trimmer. No, sorry, I'm not going to touch this and twist it a bit more or undo twists while 1000 volts are applied on that blue high voltage resistor in front of the white wire. Now that you see how this is done, the 2 volts HF calibration. This uses 1.999 volts at 20 kHz. As this trimmer is easily accessible in the disassembled state, I can use a proper trimmer tool, but even this has a reaction by just touching the capacitor, which makes adjusting tricky. For the 20 volts HF, this is much harder because only a thin metal screwdriver will fit through the PCB and able to turn the screw. I tried all plastic tools and they either don't fit or can't produce the torque needed to turn the trimmer. The problem is that the metal screwdriver massively disturbs the capacitance and therefore the reading by just being there. The only way is to adjust blindly, then remove the screwdriver, see what the display settles on and then try again until it's close enough. I don't have a good way of producing a stable 200 volts at 20 kHz. So for this one I just use 119 volts at 10 kHz. You can see what I mean. As soon as the metal screwdriver goes in, the value changes and changes again when the screwdriver is removed. So you're basically adjusting in a trial and error way. For the 1000 volts, I use just 108.8 volts AC at 5 kHz, but I'm not going to calibrate, just check. Between 106 and 107 volts, I think that's close enough. With the DMM2 so far restored and working, it might be interesting to cover some usage notes. I already mentioned that it can only show positive voltages and blinks the pol indicator, standing for polarity, at you if you have the probes the wrong way round. The minus key swaps the leads for you. From DC volts, AC volts is selected by pressing the button with a sine curve underneath, and as a result, both the plus and minus buttons are released while the volts button on the far right stays in. But if you now press ohms, the volts button is released, but the AC button stays in. The manual says, in this case the ohms takes precedence, but I think this is not a very good design and I'm not 100% sure that this works in all instances. Ohms uses the plus and minus keys to allow you to reverse the test current. Anyway, how to get the AC button out? It turns out you have to press the plus or minus key. Here I show going via volts again, but that's actually not necessary. You also realize that flawlessly operating this deceptively easy looking multimeter may require some training. Although the manual doesn't say anything, in line with other vintage meters, you can use the 2K ohms range for diode test. But hold on to your hat, the ohms voltage is 11 volts with 1 milliamp current. Also, for open circuit, that is diodes in reverse direction, you have to get used to ignore the number in the display because the OL light is on. So I can test the diode and it shows me the forward voltage. 2 diodes in series works fine too. Lighting up 3 diodes in series, of which one is a red LED, also works fine, but the forward voltage now exceeds what the DMM2 can show, so we get OL. Why stop there? 4 diodes in series, 2 of which are red LEDs. 5 diodes. 6 diodes. 7 diodes in series and we just get very dim lights. If I take the non-LEDs out of the circuit, the DMM2 can light up 2 red LEDs, 1 orange, 2 white LEDs in series. Pretty good. And to show the ohms polarity reversal, here I'm measuring a normal diode with a plus button pressed. The DMM2 shows the forward voltage. Pressing the minus button and now the meter shows OL when I probe the diode the same way. But if I reverse the leads, it shows again the forward voltage. The DMM2 has one more trick up its sleeve. Normally the input resistance in the 200 mV and 2 volt range is about 10 megohm. I'm measuring 1.5 volts and the current is about 0.177 microamps. The flickering display is a camera shutter effect. Anyway, with 1.5 volts over 0.177 microamps, we get a DMM2 input resistance of 8.5 megohm. The manual says if I release the volts button, for example by touching but not fully pressing the ohms button so it doesn't latch, the input resistance is increased to approximately 100 megohm. The current drops to about 0.07 microamps. This means the DMM2 input resistance is now 21.4 megohm, not quite the promised approximately 100, but not bad. Yet I wonder why that is. Since we are talking nanoamps here, I suspected noise and so put everything close together, used batteries as voltage source and shielding. First, when doing the math while measuring 100 millivolts in the 2 volt range with the volt button pressed, I measure again around 8 megohm. When switching to the 200 millivolt range, that stays essentially the same. Releasing the volts button and after doing the math, I get again about 20 megohm. What I expected was something like the More Pilot 17B, which I reviewed a while ago. This meter has a high Z mode, and with the values a bit fluctuating, I get between 80 and 100 megohm in the same setup. So my setup is working and the DMM2 does underperform as far as high Z mode is concerned. One needs to keep in mind that we are now measuring in the 1 nanoamp range and doing this correctly needs way more effort in setup. For example, if I remove the meter, there should be no current, yet we still see some picoamps of noise and thermoelectric effects. the plugs and the sockets act like thermocouples. I can easily demonstrate this by cooling one with freeze spray. And if I do that with the other, we have the reverse current. So measuring low currents or voltages properly is an art. With that in mind, I think the DMM2 is what it is. Maybe a good cleaning of the PCB in the input section could improve the high ohms, but I decided to leave it in peace. Finally, you may have wondered what the check 1 volt socket is for. Basically, the DMM2 delivers 1 volt on this, and all you have to do is to connect the red lead to see if your meter is working properly. That's nice, but as you can see, I'm reading 1.004, while the manual says it should be 1.000 plus minus 2 digits. But when I connect other meters to the check socket, it turns out that the voltage on the check socket is indeed slightly too high. The voltage is derived from the constant current source in the ohms section. Probably some resistors have drifted slightly, but I decided to leave that alone. Well, in the end I got this DMM2 working again, with a few niggles like high Z and check voltage remaining unresolved. Things like this are to be expected. This meter isn't a spring chicken anymore. I think it was first released in 1973. I don't know exactly how old this one is, but it's certainly very vintage. For its age, it's still in remarkably good shape. This DMM2 is now back with its owner, and I want to thank Dave for sending it in. He sent me a picture with it next to its big brother DMM3. I hope you found the repair as interesting as I did. Please contact me if you have an interesting piece of equipment that you want to send in for review or repair, or if you want to donate it to the channel. If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.